everyone. In this video, we're going to talk about graded potential and action potential. And so these are terms that we really haven't addressed before, but we could think of it as what we're going to explain is changes in membrane potential. So recall from earlier videos that transmembrane potential exists because charges are held apart across the membrane. And these charges, because they're being held apart, they hold potential energy. Resting potential is the membrane potential of an undisturbed cell, and the resting potential of a neuron is about minus 70 millivolts, meaning that the inside of the cell around the membrane specifically is negative with respect to the outside. The other concept that we want to remember is the idea that channel-mediated diffusion allows for ion movement across the cell membrane, and the different types of channels that we may encounter include voltage-gated channels, ligand-gated channels, and leak channels. And so as we get further into the description of neuron function, we'll be addressing those different types of channels and how they work. But for the purpose of this video, it will be important to remember that the ion channels must be present in order for the ions to cross the membrane. So let's take a look at a cell. And we're not going to draw it like the neuron for the sake of this video, simply because it'll be easier to show the charges. But in the subsequent videos, we will draw the neuron with its actual structure and with the ion channels where they belong. So our cell that is resting at minus 70 millivolts, we actually can describe the cell as polarized. So that negative charge inside the membrane is what dictates the idea of polarization. So even though so far we've only really addressed resting potential, it's important to know that the membrane potential absolutely changes, and it changes because it allows for cells to transfer information between each other. And we'll see this with not only neurons, but also different types of muscle cells. And so this will kind of come up again and again. The basic principles will be the same. So if we had an ion channel present in the membrane, and we had positive charge moving into the cell, or flow of positive charge into the cell, we actually would say the cell becomes depolarized. So depolarization occurs when the cell membrane potential becomes less negative, or the membrane potential moves towards zero. So if we were to represent this on sort of a graph, we could see that our starting point is at minus 70 millivolts, and we're moving in the upward direction towards the positive charge. So anything towards zero is considered depolarization. It certainly can exceed zero, and it's still depolarization that doesn't change. Now let's say that we had another ion channel in the membrane for a different ion. Instead of the red ions, we'll move the purple ions, and the purple ions are also positive charge. If the positive charge flows out of the cell after depolarization has occurred, we can call it repolarization, or the cell is becoming repolarized. So this is basically a return to rest. So we're working towards minus 70 millivolts, or actually returning to minus 70 millivolts. Now, the other option is that we can have hyperpolarization. So it can occur based on two different potential events. One is flow of positive charge out of the cell from minus 70 millivolts, or at minus 70 millivolts. So if we're starting at minus 70 millivolts and then we have positive charge moving out of the cell, we're becoming more negative. And so we refer to that as hyperpolarization, or hyper meaning like more than, so like more than polarized, hyperpolarized, more negative than minus 70, or more negative than rest, and further from zero. The other way that we can get hyperpolarization would be flow of negative charge into the cell. So again, starting at minus 70, if we had negative ions moving into the cell, then those negative ions are going to accumulate negative charges inside the cell, thus lowering the membrane potential. And so anything that's decreasing from negative 70 to more negative, again, hyperpolarization. One important thing to note is that repolarization has to follow depolarization, but depolarization and hyperpolarization, they work against each other. So you could have hyperpolarization first and then depolarization. You could also have depolarization followed by repolarization followed by hyperpolarization. So there are linear progressions, but it's not always the same way. Ions that move into the cell, when we talk about ions moving into the cell, we call that influx. Influx of positive charge, influx of sodium ions, influx of chloride ions. Doesn't really matter if it's positive or negative. And ions that move out of the cell, we refer to that as efflux. So efflux of positive charge, efflux of potassium ions, that sort of thing. And when we have movement of charges to eliminate a potential difference, we actually refer to that as current. So you may recall from an earlier video that we described current in the sense that we said electrolytes that are present in solution, or particularly in the bloodstream or in the body, those electrolytes are able to conduct electrical current. And so now we're actually going to show on a cellular level how exactly that current is conducted, what exactly is happening with the flow of ions into and out of the cell. All right, so that brings us to our description of graded potential and action potential. And these are just terms that we need to understand in order to understand the neuron's behavior. So graded potential refers to changes in membrane potential that are propagated in a graded and decremental fashion. So in order to explain graded potential, I like to use the example of, let's say that we have a person who is standing by a lake or a small pond, I guess, maybe a pond, and he's throwing rocks into the water. And by throwing rocks into the water, we know that the rock will create a rippling effect. And so we could think of graded potential as what happens in terms of the ripple effect following the rock falling into the water. So let's highlight the three important words in the definition for graded potential and then relate them to this picture. So propagated means movement from the point of stimulus outward in all directions. So we know that if we toss a rock into the water, the rings that form in the ripple effect are going to be outward in all directions. It's not like the rock falls in and then the ripple effect only goes in one direction in this pond. It's going outward in all directions, and there's no way to control that. It's going to happen. The second part is graded. Graded means that it varies in size relative to the size of the chemical input. So we could say that the size of the rock affects the size of the ripples. The bigger the rock, the bigger the ripples. The smaller the rock, the smaller the ripples. And lastly, decremental refers to the idea that the graded potential decreases in size as it moves further from the point of origin. So in the beginning, when the rock falls into the water, the ripple effect may be very strong. In fact, we can see that as the rock falls, we have a nice little, I guess you could say a small wave. And then the wave gets smaller and smaller and smaller and smaller as it moves away from that point where the rock fell into the water, the point of origin. And so this is an expected outcome. So all of these things are expected for graded potential. And so we'll kind of explain them in the context of a neuron in the next video, but it's very important to make sense of this concept and be able to differentiate it from action potential. So now let's consider action potential. Let's say that instead of a small rock, we had a giant rock. Obviously, this rock is bigger than this person, so I'm not sure how he's throwing it into the water, but let's say that he does use his superpowers, and the rock falls into the water, and we can see that the rock is so big that that initial crest from the wave is tall, and it's actually going to crash in the form of a wave as opposed to ripple away. So this is the difference between graded potential and action potential. Action potential is propagated changes in the membrane potential that affect the entire excitable membrane. They behave by the all or none principle. And essentially what that means is that when you think of a wave that's going to crash, even if you think of a wave on the beach that's going to crash, once that initiates, once the wave gets to that peak and it's sort of curling over on itself, there's no hope of it fizzling out. It's absolutely going to crash all the way. And so that's kind of the idea behind action potential, is once we get an action potential, we kind of reach this point of no return. And the point of no return means that we are making it all the way to the end, where that wave is crashing until it's gone. Now, in the context of the neuron, one thing that's important to note is that in order to have an action potential, we have to have a graded potential first. And if you think of it that way, a progression, graded potential followed by action potential, it'll be easier to keep into context what's going to be happening. So if you think about a graded potential, there needs to be a stimulus, meaning there needs to be a rock, and the stimulus needs to be strong enough that we can sort of, instead of just rippling out, we can actually make a wave. That's kind of our objective. So action potential is our objective, and you'll see that action potential is really critical in terms of how cells communicate with one another, and it's actually very, very interesting. So that wraps up our overview of graded potential and action potential, and then in the next video, we'll be able to observe how these processes play a role in neuron behavior. So I hope you enjoyed it. Thanks for watching.